So far, we have seen basic definitions about probability theory and some basic theorems that we need. Now it is time to move on to random variables or distributions, because for cryptanalysis, binomial distribution is very important to us. In order to understand how it works or what is the expected value and so on, we have to talk about random variables. So let's start. Given a sample space S, a function x from S to real numbers is called a random variable, and the range of x is denoted by Rx. So this function is mapped to real numbers, but it doesn't mean that it will the outcome can be all of the real numbers. The range of this function might be limited to a small part of the real numbers. This is why we define it as Rx, the range of x. And in mathematics, when people talk about functions, they generally don't care much about the range, but in probability theory, range is really important. An example is as follows. A coin is tossed and upper side is observed as the sample space, head or tails. Let x be the function such that x heads is 1 and x of tails is 0. So in this case, our range becomes 0 or 1. So instead of head and tails, we say zeros and ones. Actually, this is, you can see how it can be used in cryptography. For instance, when we are generating random numbers, we are actually focusing on bits. A bit can be 0 or 1. So if your random bit generator works properly, and it has a probability of generating 1 or 0 with probability 1 over 2, then your random number generator will be working correctly. So it is like tossing a coin and observing heads or tails. So another example is as follows. For instance, thinking about a function where you choose a random point in the interval 0 to 1. But this interval is the, we're not talking about integers, but real numbers. So your range now becomes 0 to 1 with the open set as the borders. So let's define a random variable type. A random variable is called discrete if Rx is a discrete set, in other words, a subset of the integer or rational numbers, or it is continuous if Rx is a union of intervals in real numbers. So in cryptography, we most of the time will be dealing with discrete sets, but normal distribution is also very important to us, and it is a continuous random variable. Now, let's talk about equivalent events. If A is an event in the range, and let B is defined as XS in this A, we have A and B equivalence events and define probability of A equals to probability of B as follows. Let me give an example. Actually, it would be useful for backgammon players. So let 2 dice be rolled. In this case, we represent the outcome of the dice with A and B. So A can be an integer between 1 and 6, and B can be an integer from 1 to 6. Of course, these are closed intervals. All outcomes are equally likely, so we are rolling a fair dice. So probability of any AB is 1 over 36, which is multiplication of 1 over 6 by 1 over 6. Let X be the sum of the results on these dices, A and B. Now the outcome can be anything between 2 to 12, and the probability distribution is as follows. As you can see, rolling 2 means that you have to roll 1 and 1 in both dices as probability 1 over 36. Rolling 3 can be possible if you roll with your first dice A is 1 and the other one 2, or first dice is 2 and the other one is 1. So the probability increases. Rolling 4 is also more likely because you can roll 1 3, 2 2, or 3 1. In this case, if you continue, rolling 7 has the highest probability, which is 6 over 36, which equals to 1 over 6. and then it decreases in this way. But here the point we are trying to make that rolling 11 has probability 2/36, and rolling 3 has probability 2/36. So these are actually equivalent events because their probability are the same. Okay. But of course, if you are playing backgammon, if you're trying to keep your distance from your opponents, making it 11 is better than 3, because in that case, rolling 3 and anything else would also, they would capture your piece. So this is why making it higher in that scenario is better. Okay, let's give definitions for probability function. Given discrete random variable x, the function pxx is actually the probability of the random variable x has the output x for all x in the range of Rx is called the probability law or probability function of x, so that probability of any event is actually greater than or equal to 0 for all x in the real numbers. And a summation of all of these probabilities would sum up to 1. So this is how we define a random variable. So if you come up with any function that satisfies these probabilities, you can say that this is a probability law. So you can actually define many different probability laws, but of course, some of them has good properties, or some of them reflect some things in real life, let's say. So we focus on those random variables, not all of them. Let's focus on the basic example, the discrete uniform random variable. A random variable x is called uniform with parameter n if the range is 1, 2, 3 to n, and the probability of observing any of these events is constant. So if you force these two definitions, then this means that since we have to have the summation of the probabilities to be equal to 1, and we have n possible outcomes, the probability of x being any of the outcomes has probability 1/n, and it is 0 otherwise. So this is the uniform random variable. It's probably one of the most used random variables, because in society everybody is trying to make everything uniform. So this is the discrete uniform random variable. So now it is time to talk about PDFs and CDFs, probability density functions and cumulative distribution functions. So far here we, when we're talking about probability function or probability law, we always focused on probability of an event, the probability of a random variable has the output x, observing the event x. But instead of making this equality, if you think about less than or equal to this value, then the function turns into cumulative distribution functions. So if we go back to our backgammon example, instead of if your aim is not to roll 7, but if your aim is to roll something less than or equal to 7, so this means that all of these cases are good for you. So the probability of observing that event actually will be the summation of these probabilities. So this is what a cumulative distribution function is. And we call it the cumulative distribution function, and we call Px the probability density function, of course. So let's move on with some summary measures. So it is a good time to talk about expected value, variance, and the standard deviation. So let's start with expected value. But since this probability theory also independently worked a lot by physicists in history, so they also independently obtain the same results. So they all say mean to it, because it's somewhat related to mass of the object, but we also call it the expected value. So given a random variable x, the expected value or mean of x is denoted by ex or mu x, and is defined as follows: the summation of probability of an event and the event that you're representing, but this representation, you know, will be summation of all over the values in the range of x. So actually, I will give an example in the uniform distribution, I think, in a minute. Let me see. Yes, we will see it here. So it is the outcome multiplied by the probability of it. So this is for the discrete case. If you have a continuous random variable, you actually replace the summation symbol with the integral symbol and the integration from minus infinity to plus infinity. Okay, so once you have the expected value, we can also compute variance and the standard deviation. So let me first give you the definition and then talk about why the expected value would not be enough for us. So the variance of x is the number sigma square, which is denoted by variance x, because we will call sigma the standard deviation. So this is why variance is sigma square. So variance is actually the expected value of the random variable minus the square of its expected value. And if you perform some basic operations, you can also observe that the variance is also equals to expected value of the square of the random variable minus the expected value. But this time the square is not above x, but above the expected value. And we have some properties about variance. Variance of a random variable and plus a random real value for any real number k is actually equals to variance of x. So shifting the values doesn't change the variance. In other words, if you take the random variable on the xy coordinate and move it to other place, the variance would not change. And variance of k multiplied by x means that x would give you k squared times the variance x. So multiplying the random variable with some value would actually result variance multiplied by the square of that value for any k, which is a real number. Finally, as I told you, we define the standard deviation as the square root of variance of x, and you obtain this result. This is the definition. So now we know these definitions. Let's see how they work. So let's look at the discrete uniform random variable. Recall that we define it as the having the output from 1 to n with probability 1 over n. So observing any output is equal or likely. So we said that the expected value is k from 1 to n, k times its probability, and its probability is fixed. It is 1 over n. Since this is a summation over k, this 1 over n is just a constant. You can take it to the beginning of the summation and like this. And then if we recall some calculus, summation from 1 to n would give you actually n multiplied by n plus 1 divided by 2. And we also have 1 over n at the beginning. These n's cancel. And it says that your expected value for a uniform random variable is 1 plus n divided by 2. But as you can see, this is the summation of first and the last entry divided by 2. So the middle value is your expected value, which is not surprising. Similarly, we can calculate ax squared. So this time instead of k, you have k squared. You perform the same trick, take the 1 over n. If you recall from calculus, this summation k squared with k is from 1 to n will give you n times n plus 1 times 2n plus 1 divided by 6. Again, n's cancel out. This is your variance. Sorry, this is ex squared. I told you that we can obtain variance by subtracting this from this. So if you subtract this from this squared, you get n squared minus 1 divided by 12. And actually, if you take the square root of this value, it will give you the standard deviation. So you might think that why we need these definitions, I mean, why the expected value is not enough. Recall that, you know, for our students, for the exam outcomes, they're always interested in the mean of it, the average value. So For instance, if I tell you that the average value in an exam is 50 out of 100, you would get a basic idea about what the average of the students are performing. But individually, this doesn't give you much definition, because assume that in an exam where every student got the grade 50, so that the average is 50, but in a different scenario, assume that half of the students scored 0 and half of the students scored 100, but their average is also 50. So seeing the average value, in our case, the expected value, does not tell you how people get close to this expected value. But the standard deviation actually tells you that if the standard deviation is small, this means that people got very close to the expected value. If it is large, a lot of people deviated from the expected value. So you can see very high and very low grades. So these measures are really important. This is just a introductory lecture about probability theory, but these topics have a lot of uses in many different areas of science.